The mystery of light. Is it a wave or a particle? For centuries, the nature of light has puzzled scientists. Is light a wave, like ripples on a pond, or is it a stream of particles, like tiny bullets of energy? Early scientists like Isaac Newton believed that light was made of particles. This explained how light traveled in straight lines and bounced off surfaces. However, in the 19th century, experiments showed that light could also behave like a wave. Light could bend around obstacles and interfere with itself, just like waves in water. This debate over the nature of light wave or particle raged on for years. It seemed impossible for light to be both a wave and a particle at the same time. Yet, the evidence was mounting that light possessed a dual nature. This realization marked a turning point in our understanding of the universe. It paved the way for a new era of physics that challenged our classical intuitions. Unmasking the dual nature. Key experiments and their significance. Two groundbreaking experiments played a pivotal role in revealing the dual nature of radiation and matter. The first was Young's double-slit experiment conducted by Thomas Young in 1801. Young shone light through two narrow slits and observed the pattern it created on a screen behind. If light were made of particles, one would expect two bright bands on the screen, corresponding to the two slits. However, Young observed a pattern of alternating bright and dark bands, known as interference fringes. This phenomenon could only be explained if light behaved as a wave. The second pivotal experiment was the photoelectric effect, discovered by Heinrich Hertz in 1887, and later explained by Albert Einstein in 1905. The photoelectric effect refers to the emission of electrons from a metal surface when light shines on it. What puzzled scientists was that the energy of the emitted electrons depended not on the intensity of light, but on its frequency. This could not be explained by the wave theory of light. Einstein, drawing upon the work of Max Planck, proposed that light consists of discrete packets of energy called photons. These photons, he argued, behave like particles when interacting with matter. Einstein's explanation of the photoelectric effect revolutionized our understanding of light. Embracing the paradox wave-particle duality. The experiments of Young and Einstein, along with other observations, led to a profound realization. Light exhibits both wave-like and particle-like properties. This concept, known as wave-particle duality, is a fundamental principle of quantum mechanics. It states that all particles of matter and energy, not just light, exhibit both wave-like and particle-like behavior. Wave-particle duality is a difficult concept to grasp, because it defies our everyday experience. In our macroscopic world, objects are either waves or particles, never both. However, in the quantum realm, the distinction between waves and particles becomes blurred. The way a quantum entity behaves depends on how we choose to observe it. If we set up an experiment to measure wave-like properties, we will observe wave-like behavior. If we set up an experiment to measure particle-like properties, we will observe particle-like behavior. Dual nature in action, from everyday life to cutting-edge technology. The dual nature of radiation and matter is not just an abstract concept confined to the realm of theoretical physics. It has profound implications for our understanding of the universe and has led to numerous technological advancements that shape our lives. One of the most ubiquitous examples is the electron microscope. Unlike traditional light microscopes which use visible light to illuminate objects, electron microscopes use beams of electrons. Since electrons have a much shorter wavelength than visible light, electron microscopes can achieve much higher resolution, allowing us to visualize objects as small as atoms. Another remarkable application of the dual nature is in solar panels. Solar panels convert sunlight into electricity, harnessing the photoelectric effect. When photons from the sun strike the solar panel, they knock out electrons from the semiconductor material, generating an electric current. This technology is becoming increasingly important as we transition towards renewable energy sources. From medical imaging to telecommunications, the applications of the dual nature of radiation and matter are vast and ever-expanding.